away from the definition of the set. Okay, interior of A, it's going to be the set of all the points belongs to R square, where x squared plus y squared greater than 1, and y is greater than or equal to x squared, which is the definition of this area. This is open, no boundary included, and every point has a neighborhood entirely inside A. Interior, open lens, region inside the unit disk, and above the parabola. The exterior of D. What are the points exterior of D? All points that lie outside the unit circle or below the parabola. كل البوينتس اللي outside the circle أو below the parabola and not included in the part of A that's exterior. The boundary, it's gonna be the circle xy squared. X squared plus y squared equal 1, where y equal to x squared, which means this is the boundary of the upper half. And also, it's gonna be apart from the parabola y equal x squared, where you have x squared plus y squared less than 1, so this is the other boundary. And also the limit point for the sequence, which is 0. So this sequence, which already exists in here from 1 and around up to 0, so this also point at the 0, this is also considered a boundary of this set. Okay, perfect. Once more, he needs the closure. So the closure of this set will be the open region, then the boundary of the set, then the points 1 over n, and the 0 point of this sequence. So simply the closure of this point, it will form from all the points that's in interior, the boundary points that exist in here, plus the accumulation point, which is 0. So it's D union the boundary of D union the 0 point. The derived point, remark, all the points which inside the region are isolated points. Because if you have an half and half, or 1/3 and 1/3 and so on, these points already exist in here, and they are all of them isolated points inside your area. The only accumulation point actually will happen when 1 over n tends to infinity, it's gonna go for 0. So although 0 is not within this interval, but it will be involved through this your set once it starts accumulating up to infinity. So that's the limit for this sequence. D dash, as I told you, D dash, which is the derived part, lens region, union boundary, union 0. The isolated point, the points 1 over n are isolated, each has a neighborhood of no other points from the set. Is it open? No, because it contains an isolated points. Is it closed? No, because the boundary is not fully included, as I told you, the upper part or the upper boundary, and also the limit is not in the set of Z. This is about the limits in sets in general, and we will talk about, I want to focus now, or to start talking about limits. So all what we talked previously in the topology about the interior, the closure, the boundary, the exterior of a set, all of this, we needed them in order to go through the definition of the limits in multi-variable function. Let me start first with the difference between the limit in one dimension and in one variable functions and the limit in multi-variable functions. If we start with the limit with one variable functions, for example, if I have y, which consists of, let's say, 2x plus 1, where x is less than 1, and y equal to x squared, where x is greater than or equal to 1. The limits usually for an f of x, if I want to find a limit of a certain value, let's take this example, limit x tends to 1 from the right. So if this is the x-axis, that's 1. We are talking about x less than 1. We will use here f of x, which equal to 2x plus 1. On the other side, we will have f of x equal to x squared. So that's the right and that's the left. So if I want to take the limit of x tends to 1 positive, I will be dealing according to this definition with y equal to x squared. So here I will have this part, f of x equal x squared, and once you start substituting, it's going to be 1. This is the right side limit. If I'm dealing with the left side limit, so it's also it can be looked at as a combination point of all the set from the right, it will approach 1. This is why you have taken the accommodation point and the previous definitions. Limit x, okay, tends to 1 negative for the negative side. In this case, I will be using this function, which is 2x plus 1. Once you start substituting, you will have 3 as a limit for the left-hand side. Once you have limit of x tends to 1 positive, that's not equal to limit of x tends to 1 negative, then there is no limit. And your limit doesn't exist. There is no value for this limit, or this limit doesn't exist. On the other hand, if I just make a small change or minor change, let's say or discuss the case fy equal to 2 over x minus 1 and x squared, where x is less than 1 and the x is greater than or equal to 1. If you try to get the limit of x tends to 1 in negative, it's going to be a 2 over x minus 1, which is going to end up having 1. A limit of an x tends to 1 in a positive of an x squared, which is going to be 1. And in this case, you will have your limit, since the left-hand side or the left side equal to the right side, which is called lateral limits of one variable function. So if all I have to do, and there is no other way to find this limit, it's really very simple, just only one direction. It is the lateral one in the case of one variable functions. Just to discover the value of your limit, I will get the right side limit and the left side limit will be equal to each other. Then I have a limit where the limit exists. If not, the limit doesn't exist. As I told you, a very close example for 2x plus 1, which is less than 1, x squared where x is greater than or equal to 1. Similarly, like the first is 3, the second is 1, it's not equal to each other, so this limit doesn't exist. If you make this minor change, 2x minus 1, you will find the left and right equal to each other, and hence you will have your limit. On the other direction, if you are talking about, or in the case of two variable functions, or start in multi-variable functions, not just only lateral functions, the idea will be much more complicated, or it's not going to be that easy, because you can access a point in the domain from plenty of curves, or using plenty of curves. So if this is the y-axis, and that's the x-axis, and that's the point A and the B, and you want to approach getting the limit of x and y going near A and B for the function that we have f of x and y, which is going to equal to L, this limit will need further investigation, as we will see. Because simply, you don't have just only one way to approach this point. There is variable, it's a region. So it's not just only the left and right directions. These are all could be directions that you approach A and B. And if there is just only two curves explaining this function that they don't meet or equal to the same value, it's not gonna be exist. All of this are written in here. Let's say you have a function of two variables, f of x and y, and you need to get the limit of f and xy, where xy tends to a and b. So this is the limit, xy tends to a and b for function f of x equal to L. All the points gets arbitrarily close to a and b. The function value of x gets arbitrarily close to the point of Unlike the functions, this is very, very important. Unlike the functions of one variables, where you approach from left and right. Here in one variable functions, limit from the left, limit from the right, and they equal to each other, then your limit exists. No, it's not going to be that easy. In two variables, you can approach AB from infinitely many methods. أقدر أوصل للAB from infinitely many methods. Along lines, parabolas, curves, spirals, whatever, which will pass through A and B. Okay, for the limit to exist, the value of xy must approach the same number from all curves. If that's the condition for the limit to exist. If you have or find just only two different passes that give different value, the limit doesn't exist. This is the problem of investigating the limits in two dimensions, unfortunately. Okay, let's look to this point or to this example. Let us express or try to see the limit. Here we go. That's the limit of x and y tends to the origin for x squared plus y squared. Okay, very, very simple. Through, let's do it through the x-axis, okay, the x-axis, the y-axis, okay, and y equal to x, for example, even for y equal to a sine of x. Let's try these curves. If I then try the x-axis, which means y equal to 0. So if I want to do this, I will start to substitute on my limit by this information, which will lead to that according to this result, this is going to be the case. This is the limit of x, just only replace y equal to 0, so x will tend to 0, and you will have x squared, so the result is 0. If I use the y-axis, which means x equal to 0, I will use this fact also and substitute in this problem. And once you both insert x equal to 0, all you will end up having, its limit y tends to 0 for just only y squared, and you will have the same result from this one. If I used y equal to x in here, it means I will replace every y by x. And so the limit will change now, will be limit x tends to 0, and you will have x squared, and replacing y equal to x, so it's gonna be another x squared, which is gonna be 2x squared, taking the limit of x tends to 0, which you will end up having 0. Even if you use y equal to sine x, you will have, and make this substitution here, replacing y by sine x, you will get the limit of x tends to 0 over x squared plus a sine square of an x, and the result will be 0. As you can see, this is number 1, number 2, number 3, number 4 curves. All of them, they have the same results. So the limit of x tends of x and y, of x and y, tending to the origin 0 and 0 for x squared and y squared, the result will be 0, and the limit already exists for this problem. If I try this once more, but actually, okay, if I try this once more, let me first do the explanation and I will show you another example. So, if y equal to x, y equal to 0, even y equals sine x, you will get the same result once you substitute, as we saw exactly it will equal to 0. Okay. Here's an example of a limit doesn't exist, which is very, very famous example. xy divided by x squared plus y squared. Try to approach 0 and 0. Let's do the limit. If I try to approach 0 and 0, so you will have, okay, by using the following curves. Let's say for y equal to x. I will consider the curve y equal to x. So if I replace every y by x, this is going to be x squared over 2x squared. Taking the limit here for x tends to 0, you will end up having a half. In a similar manner, if you go for y equal negative x, and you make this substitution, so it's going to be negative x squared divided by, once you make the substitution, x squared plus x squared, you will have negative x squared with x squared, so it's going to bring to negative half. Here the limits doesn't equal to each other, and so it's not gonna, the limit doesn't exist. Once more, that's the condition for a limit in multivariable function to exist. In case of functions of two variables, as I told you, let D be an open set of R2, f such that D into R of x node y node. This is the point. These are the curves, as I told you. In order to have this limit to exist, all the values must equal to the same value of your function. Otherwise, the limit is not going to exist. The values of x, this is exactly the same, but I thought to write it once more for you to be just crystal clear for you. Okay? This is not the full limit, it is a partial test of the limit by restricting the path. Of course, in R2, I can restrict special passes or particular passes, and they take the limit within these passes only, just to check. In multivariable calculus, as I told you, approaching from different directions or curves can lead to different values. Unlike one variable, you have infinitely many directions and passes. For this problem, x squared y squared, we want to investigate the function. Okay, in the case of the y-axis, we already did that, it's going to be 0. For the y equal to x is going to equal to half, since they are not equal to each other, so the limit doesn't exist. In the case of parametric functions, the case will be easier because x will be defined as a function in t and y will be defined as function in t. So once you start substituting or working out your limit, it's going to be much easier. So let's see the regular curve in the plan with a parametric equation, x as an x of t, and it equal to y of t belongs to the interval. Let d belongs to R2 be an open set, so you will have x, the x component as a function in t node, and y is another function in t node. Once you start your limit, this is the limit, and this is the specific curve. That's the representation of the curve, and of course you are going to use just only t equal to t naught. The graph over here emphasize how it's working. This is the value of x and t and y of t, and this is the projectile of a certain point, and it's going to be in here, that's the f function. If both of these two functions are approaching x node and y node, then the representation of these two functions in parametric, they will be approaching the point L, as you can see. That's the definition. It's called directional limits. A limit along the line is called the directional limits. The lines passing through the point X are given by the equation. That's if you have a line equation expressing the relation in parametric notations. Okay. Here, for example, and that's a normal example. It's not about the parametric, but just investigating one small negative xy divided by x squared y squared through the various curves, the x-axis. Here calculate the direction limits at the point 0, 0, along the x-axis, the y-axis, and along the lines xy and x minus y, as we did on this problem, but we will do the same with that problem, as you can see. For x equal, for the x-axis, I will use y equal to 0. So y equal to 0, you will end up having the 0. For the y-axis, is going to be the same. For x equal y, you will have a half. For x equal negative y, you will have a negative half. See, these are the results which are equal to each other on these two curves. But once you go through half x equal to y or x equal to minus y, so the limit doesn't exist for this problem, since you have two, at least two curves that they don't have the same result, as you can see. Okay. Our stay today, I'm not going to enter Cauchy definition of two variables. It's not what we had today. Remember that we started in the early morning by finalizing the part of the parameterization problems, we really did solve most of them, actually all of them for this for their list. Then we ended up the chapter 7, which included some of the topological expressions and the symbolization of these expressions, either the open ball, the interior of a set, the exterior of a set, the closure, the boundary or the frontier of a set, and the differences between them, the intersections and so on. And we started on the topic of taking limits in multivariable functions, how to go through them, and the obstacle that it's hard to find a limit for a multivariable function because it must have the same result from all the same curves. But sometimes you will have this if you have just only certain curves or restricted curves, the limit may exist. Thank you very much. I hope you enjoyed the lecture of today. I know it is condensed and it's full with a lot of information. Please do go through them once more. Use your pen, as I always tell you, and try to resolve those couple of examples. Hopefully, inshallah, next lecture, I will go through the rest of this part with plenty of problems within application on this part. Thank you very much and wish you the best forever. Thank you. Enjoy your day. Thank you. Bye-bye.